right, so moving through chapter 16, and again, you should have this review sheet here that highlights the 5 things that are important from this chapter. We've already covered reaction rates and rate expressions, and again, that has to do with relating rate to a chemical equation and the disappearance of reactants or the appearance of products. We've done sample problems dealing with the rate law and using the method of initial rates to determine that rate law. So again, that's using this kind of a flow chart to think about determining initial rates, reaction orders, and then rate constants. So the next 3 sample problems deal with what we call integrated rate laws. And integrated rate laws are important because it allows us to ask questions about time. So how long will it take for a certain process to happen? What is the concentration of a certain reactant after a given amount of time? And in addition, we can look at plotting the concentration of a certain reactant as a function of time in a variety of forms, either directly as a natural log or as an inverse, to use that to determine reaction order graphically. So table 16.5 is a great kind of summary table from your book that shows the different equations and graphical representations that you'd have for 0 order, 1st order, and 2nd order processes. So the next 3 sample problems are going to kind of work through how we can think about using integrated rate laws. And what I hope you'll see is that we introduced chapter 24 first, which dealt with nuclear chemistry, which is 1st order kinetics, to get us kind of started with this process. And so the 3 sample problems that we're actually going to work through all deal with 1st order processes. So the first sample problem is 16.5, and this has to do with determining the reactant concentration after a given time. So remember, we're talking about being able to think about time with an integrated rate law. And so this problem says that 1,000 degrees C, cyclobutane decomposes in a 1st order reaction. So all of these problems have to either directly by saying 1st order, 2nd order, 0 order, so forth, tell us the reaction order, or in a little bit more challenging problem, it might give you a little bit of information. It might give you a rate law where you'd have to infer the reaction order from that, or some other type of data that you have to first make an inference in terms of what the order is. But we need to know the reaction order for this because that's the only way we're going to be able to pick which set of our integrated rate law equations to choose, 0, 1st, or 2nd order equations. So this tells us 1st order, and it gives us the rate constant, a very fast rate constant. And so they tell us that cyclobutane is decomposing to 2 molecules of ethylene, but we really don't even need to know what the chemical equation is doing here. We just need to know that it's a 1st order reaction. Here is the reactant, and they give us the rate constant. So remembering, and this is like chapter 24 problems, with these problems there's basically 2 equations that are relevant. The natural log of how much you start out with versus how much you end up with at a certain time is equal to the rate constant times the time that has passed. And then the other equation that we need to think about is that the half-life is equal to 0.693 over the rate constant. And again, the reason we need to use this equation is if they didn't give us the rate constant directly, we'd need to use the half-life in order to find what the rate constant is, right? Because we can rearrange this equation to be that. With this problem, they actually give us the rate constant directly. They give us at 87 per second. They tell us that the initial concentration is 2 molar. So again, they give us the rate constant here. They tell us that 0.01 seconds has passed. So again, they're giving us that piece of information. And we'd like to know what the concentration is at that time. So we're going to be solving this equation for the concentration at time t. So again, if we put in the information that we know here, natural log of 2.00 molar over what we want to find, the concentration at time t, equals 87 reciprocal seconds times 0.01 seconds. And again, it's really important to note that right now these units match, so we could use the information provided for us directly. Kind of this problem becomes a little bit more challenging if the rate constant and the unit of time that's passed do not have the same units. So it's always important to look at your units. In this case, they do match. And so again, we're solving for something that is part of the ln of a over b type term. So a way to kind of get rid of this is we can take e to the both sides, and 87 times 0.01 is 0.87. So e to the ln of something gives you that something. And e to the 0.87 equals 2.4. So again, then solving for a sub t, so the concentration at time t is 0.83 moles per liter. So if we think about this, this makes sense. It's not larger than 2, right? We shouldn't end up with more reactant as the time proceeds. So kind of ballpark things, ask if things make sense, see if it is reasonable in terms of what to think about. Even thinking here that, we'd have 87 of these reactions happening every second. So if we went through 1/100th of a second, okay, we might have, in thinking about how much has happened, it's kind of reasonable that we've gone through close to 1 half-life. So about half of the material is gone. Okay, so that answers part A. What is the concentration after 0.1 seconds? So part B asks us to think about the fraction that's decomposed. So remember, anytime you think about fraction, think about part over whole. So the whole is always going to be what we started out with. The question is what do we want up here? And there's two things that we need to think about. We can ask about the fraction remaining, and if that's going to be the case, we can basically just take, this is the amount that's left, right? Concentration after 0.01 seconds. This is the amount that's left. So if we want to talk about the fraction remaining, that would be a sub t directly over this. If you want to think about the fraction that has reacted, or in this case, it's a decomposition reaction, so this is the fraction that's decomposed, we need to take the difference of how much we started with and how much is left. So that's going to be a sub 0 minus a sub t. So in this case, we want to know the fraction that's decomposed. So we want to take a sub 0 minus a sub t over a sub 0. And we had a problem like this in chapter 24, where we had to think about the fraction of a certain radioactive nuclide that had decomposed. We didn't want to know the fraction that was left. We wanted to know the fraction that was decomposed. So we needed to take the difference between the amount that we started with, which in this case is 2 molar, subtract what has reacted, which is 0.83 molar, and put it over, again, the whole, which is what we started with. This ends up being 0.58 as a fraction, which means that 58% of it has decomposed. And again, thinking of 87 of these happening per second, if we've gone through essentially 1/100th of a second, we've gone through enough time that it's approximately 1 half-life. So about 58% of it has decomposed.